Okay, in this lesson we will talk about image characteristics created by the thin converging lens at a different object distance. So these are learner's outcome. Basically, we'll understand and apply characteristics of image formed by lens with a particular focal length of f when the object is at different distance. So some prior knowledge, just a bit of recall or recap. So to identify the location of image formed by a thin converging lens, we just need 2 out of the 3 light rays. So the 3 light rays are PCF. P means parallel, the light ray that's parallel to the principal axis. C, a light ray that passes through the center of the lens. And F, or passes through the focal point before the lens. So we just only need 2 out of 3 of this light ray to locate an image. Generally, this is the example. So if the object is at a certain distance away from the lens, you just draw one light ray that is parallel to the principal axis, and you will go towards the focal length. And another light ray that passes through the center of the lens. You find that the intersection point here will indicate where the image will be. So this is where the image. So generally, this is how you draw your image or locate your image. So right now we'll explore different object distance to the lens. So the light rays of the light ray diagrams drawing methods are actually very similar regardless of the object distance to the lens. But of course different object distance will lead to different location of the image where the light rays will intersect. And these intersections are the location of the image and will determine what are the characteristics of these images. Images can be classified into the following characteristics. The type, whether is it a real image or virtual one. Magnification, whether the image is larger than the object, is it same size or is it smaller than the object. Then orientation is whether is it upright or is it inverted. Just a note on calculation of magnification. It's just a comparison of the image size versus the object size. So the formula is generally image height over object height. Alternatively, you can also use image distance over object distance. The magnification value, if it is greater than 1, means that the image is bigger, is enlarged than the object. And if it's less than 1, then image is smaller than the object. So before we deal with the specifics object distance, let's look at some general pattern. So we start our simulation of an image formed under the lens for object distance that's initially far away, but get closer to the focal point of the lens. Okay, so right now this is the lens, this is the object, and this is the image. So you can see that right now the image is actually smaller than the object. Okay, but let's look, and this was what was the drawing, a line that's parallel to the principal axis, and then a line that's parallel that passes through the center of the lens. So this form where the image will be. Let's just move it closer and see what will happen to the image. You notice that the image, as it gets closer and closer, the image will get bigger and bigger. Okay, right now this is obvious that the image is bigger than the object, so it's magnified. So as it gets closer and closer, you find that it gets bigger and bigger, and of course right now you don't see it. So from a simulation, we know that the further the object distance, the smaller the image form. And image distance and image size is actually proportional. A smaller image has actually a shorter image distance, or a larger image has a longer image distance. So you can rewind and look at it, see whether is it true. Okay, but I would like to emphasize this again. The further the object distance, the smaller the image, which means that the closer the object distance, the larger the image. So this is the first case. Okay, you find that right now we are a bit more specific. It's the object beyond 2f. Okay, that means there's 2 times of the focal length f. So if the focal length is 10 cm, anything that is more than 20 cm means that it is more than is under this category. So if you just apply accordingly the parallel and the center, you find that the image will be in this manner. So of course notice that in this case for 2f, the image is actually smaller than the object. The characteristics is it is real, okay, and it is inverted, and it is diminished. Diminished means smaller. Real means that the actual light ray actually intersect after passing through the lens. They converge and intersect at a particular point, and this is where the image will lie. So what is the application? Okay, is a camera, okay, or handphone camera or camera, doesn't matter. It is because generally the picture that you're trying to take is that the object is larger than the image formed inside the small camera. Okay, so this is application. So from a big object, you translate the image to a small one to be captured in a camera. Then next, object at 2f. So this is very specific. It is at 2f only. So at 2f, if you do the same treatment, you find that in this case, the image will have a very special characteristics. It is still real, it is still inverted, but it is in this case, it is the same size. So it is exactly the same as the object. So magnification is 1. So let's bring it closer still. So right now the object is in between f and 2f. So if f is here, this is 2f. So object is over here. You find that if you do these characteristics, the image of the object is projected much further and the image is enlarged. In this case, it is still real, it is still inverted, but this time round it is magnified. Okay, so what is the application is that you take a small object, you want to make the image bigger, so it is actually one application is projector. Right now, what about object at f? So this one is very specific. If its object is at f, you place the object at a focal length, what will happen is that if you try to draw the parallel line, that parallel to the principal axis, and you try to draw the center, you'll notice that the light ray actually never intersect. Okay, you will never intersect. So it means that the image is considered to be at infinity. You wouldn't get a focus image, and you will just get a blur parallel light image. Right now object at less than f, so we do the same thing, and this time round you find that the parallel and the center light ray, they are not even parallel to one another, but yet they diverge. So in this diverge, definitely they will not be able to converge or provide an image that's over here. Okay, so but what will happen is that if we place our eye that's over here, okay, to see the image, we will start to perceive that even though the light ray is actually going this manner and in going like this, refracted by the lens, and the light ray is going in this manner as passing through the center of the lens, to our eye will perceive that the light ray actually comes from here. Okay, so the dotted line is actually stating that this is a virtual light ray. So the light ray actually doesn't exist, but we think that the light ray actually comes from here, and the light ray seems to come from the center from here. So if it diverges over here, it means that it would some point converges at this. So this is where the image seems to come from, and the dotted line means that it is a virtual image. So this particular image is actually virtual, and it is upright, and in this case of course the image is bigger than the object, so it is considered to be magnified. So what is the application of this? You find that it is a magnifying glass. So originally the B is not as big, but under the magnifying glass it will appear to be much bigger, but it is a virtual and upright image. Okay, the last category of distance is object at very far away, as considered to be infinity. So let's consider this huge object. Okay, this huge object at some very far away, it will emit out some light ray that is not parallel. Okay, and after passing through a huge distance, okay, you find that the light ray will be considered to be parallel, okay, because it's so far away when it strikes the lens. So this is a very huge distance. Okay, this is considered to be infinite in terms of the distance. So the key point is that light rays from infinity or very, very far away is assumed to be parallel to each other when they strike the lens. Okay, so object at infinity or very, very far away. So what you need to do is to choose one light ray that passes through the center of the lens. And since just now we discussed that light rays from infinity would be parallel to one another, you choose another light ray that is parallel to this center of the lens, and it is also parallel to the it is also touching the focal point of the lens. And we know that passing through the focal point of the lens, after it hit the lens, it will be refracted so that it's parallel to the principal axis. And in this case, the intersection point is over here, which is where the image will be formed. And you'll find that the image form will be at the focal length. Okay, so the image form will be actually at the focal length. Okay, and it is real, it is inverted, and is considered to be diminished, because remember the object is actually very, very far away, and it's very, very big object that's very, very far away. So compared to this image over here, is much smaller than the actual object. So what is the application of this is that it's the telescope. So generally telescope is used to see objects that's very, very far away, and of course very, very big, such as planets, stars. So a summary of the image of characteristics. So generally anything that is more than f will be real inverted, but more than 2f will be diminished. In between f and 2f is enlarged. At 2f is same size. At f is the image will be formed at infinity, very far away. An object at infinity forms image at f, which is over here. So anything that's less than f in front of a lens would be upright and enlarged. So generally that's all for now.